Hi guys, Mrs. Rossi here. We're going to go over some more information about electrons and atoms. You have your note sheet to collect information on as I'm talking and going through this. At any time, if you think you missed something, need to go back, just pause or rewind this presentation if you need to. The first thing we're going to be talking about is a little bit of review. So all of these guys are atomic theory scientists that we've talked about earlier in the school year. John Dalton, J.J. Thomson, Ernest Rutherford, and Niels Bohr. You should remember Dalton is called the father of the atomic theory because he was the first one to do experiments and actually said atoms do exist. J.J. Thomson was the first guy to disprove Dalton, and he discovered the electron. Ernest Rutherford went even further than J.J. Thomson, and he did more experiments and he discovered the nucleus. He was the first one to say that electrons surround the nucleus. Niels Bohr did even more research, and he was the first to say that electrons exist in energy levels around the nucleus. So this is a really big deal because Niels Bohr is the model that we've been using up in class until this point. You should know, though, that the Bohr model is nice because it's 2D, but it doesn't accurately represent what's actually going on in the atom. Today's model of the atom is called the quantum mechanical model or the electron cloud model. Remember, the electron cloud is the region of space that electrons are likely to exist. That doesn't mean that we know where they are 100% of the time, but using quantum mechanics, which is the name where the name quantum mechanical model comes from, you can predict where an electron is likely to be found. The Heisenberg uncertainty principle, so Werner Heisenberg is one of the people that worked on the quantum mechanical model, predicts using mathematics where you can find electrons 90% of the time. So using these complicated math equations, we can figure out the location of an electron with 90% certainty. If you look at the image over here, you can see the nucleus of the atom, and then all of the little dots and specks you see around there are likely places to find an electron. So this is your electron cloud out here. The quantum mechanical model does get a little bit more complicated than the Bohr model, which kind of makes sense because it's a little bit more accurate, or way more accurate, and it uses a lot of math. We're going to be focusing on what it tells us about electrons. The first thing you need to be aware of is the principal energy level. The rows on your periodic table, the periods that go across, represent your principal energy levels. So the principal energy level is denoted by the letter N, and it always equals a whole number. So N can equal 1, that's the first row on your periodic table. N can equal 2, that's the second row. N can equal 3, that's the third row. N can equal 4, and so on all the way up. Within these energy levels, there are sublevels. So these sublevels are different shapes. And this different shaped region gives us an idea of where those electrons are able to exist. Those sublevel regions or orbitals are where you can actually find those electrons, where that 90% certainty gets to be a little bit better. So the different orbitals have different shapes. S orbitals are spherical. P orbitals are dumbbell shape or kind of look like infinity signs. D orbitals kind of look like clover leaves, and F orbitals kind of look like flower bursts. So obviously we are dealing with three-dimensional shapes, and I'm asking you to draw them on a two-dimensional surface. So just do your best to sketch out these on your note sheet. All right, so this chart is a little bit of a summary of what we've been talking about up until this point. We have our principal energy level. So remember, N represents your principal energy level. And 1, 2, 3, 4, 5, 6, 7, it keeps going depending on the number of rows or based on the rows on the periodic table. You should see a correlation between the energy level and the number of sublevels that exist. So in that first energy level, in that first row of the periodic table, there is one sublevel. That sublevel is the 1s sublevel. So it's energy level 1, and it just has that spherical shape. In the second energy level, there are two sublevels. There is an S sublevel. So in the second energy level, there is another S, and then there is also a P sublevel. In the third, there's three sublevels, which means there's an S orbital, a P orbital, and a D orbital. In the fourth, there's 4, which means there's an s, a p, an f, and a d orbital. Depending on how many sublevels you have over here, you can fit a different number of electrons. And it should make sense based on what you already know about atoms, that as the energy level increases, that you're getting further away from the nucleus, and that you also are gaining the number of electrons that can fit around that atom's nucleus. Here's just a picture representation of what we've been talking about. This would be your first energy level, just your 1s, and then here's your p, so more regions of space for that to exist. Here's your d. You can see on the 3D shapes where they can have electrons existing in these little bubbles. And same thing with the f. So your principal quantum number is always the same as the number of sublevels within that energy level. Hopefully you saw that on that last chart. To figure out how many electrons can fit in that principal energy level, there's a formula you can use, so you don't have to count it out every single time. The formula is 2n squared. So this is how you figure out the maximum number of electrons that principal energy level can hold. For example, if you're in that first principal energy level, so n equals 1, you would do 1 squared times 2, which gives you 2. If you were in the second energy level, so a little bit more energy, you would do 2 squared, which is 4, times 2 to give you 8. If you were in the third principal energy level, 3 squared is 9, times 2 gives you 18. If you were in the fourth, you would do 4 squared, which is 16, times 2, which gives you 32. So 2n squared is the formula you use to figure out the maximum number of electrons that can fit in that energy level. So here's a little summary of everything that we've been talking about so far. N is your principal energy level. It is always a number, and when you're writing out your electron configurations, it always comes first. Your sublevel is a letter. It tells you what shape orbital you're dealing with. Your sublevel has those orbitals in it, and it tells you the region of space that electrons are likely to be found. Within each orbital, so within each little bubble that you have of that sublevel, you can only fit a maximum of 2 electrons. So in any s orbital, remember that's our spherical shape, you can fit a maximum of 2 electrons. Within a p level, it doesn't matter what energy level it is at, so 1, 2, 3, 4, 5, 6, 7, you can fit up to 6 electrons because there's 3 orbitals, so 3 little lines or 3 little bubbles of space, 2 electrons fit in each one. In a d orbital, a d sublevel, you have 5 orbitals, which means a maximum of 10 electrons can fit. So it doesn't matter what energy level you're at, if there's a d sublevel, you can fit up to 10 electrons in there. With an f sublevel, you have 7 orbitals and up to 14 electrons can fit. So we started talking about electron configurations and atomic orbitals. There are certain rules that you have to follow in order to fill these and represent these electron configurations correctly. The electrons just don't fill in randomly when they are building an atom. So the next thing we're going to talk about are the rules that govern electron configurations. First rule is the Aufbau principle. If you think back to the reading that we did in class, it should make sense, and you should remember this word. So the Aufbau principle states that electrons enter orbitals of the lowest energy first. If orbitals become full, they do go up to higher energy levels, or they work their way through that current energy level until it is full, and then go up to the next energy level. So in this case, n equals 1, which is closest to the nucleus, this orbital energy level would fill first. Once that one's full, then you go out to the next energy level. That one would fill second. Once it's full, you go out to the third one, and so on. In this case, this is an orbital diagram, and it shows the sublevels in a little bit of a different way. The big number on the outside is your principal energy level, and then you see the sublevels denoted by the letters. So the 1s is your lowest energy principal number and sublevel. So this one will fill first. 2s, according to our arrow on the side, is next up in energy. 2p would be after that, and then 3s, then 3p. Then careful, because 4s and 3d are close. It goes 4s, then 3d. Notice that they're very close in energy, those two, but it does go 4s, then 3d. The next rule that electrons have to follow is the Pauli exclusion principle. It says that an atomic orbital may describe at most 2 electrons. For example, if either 1 or 2 electrons occupy an s orbital or a p orbital. So to occupy the same orbital, those electrons, if they're both in there, have to be spinning in opposite directions. We use arrows to represent electrons in this case, and the spins in opposite directions, it's either an up arrow or a down arrow. By convention, we always do an up arrow first, and then if there is another electron in that orbital, then we'll use a down arrow. So here's an example of what it will look like filling in a diagram. In this case, we have 1, 2, 3, 4, 5, 6, 7 electrons. All right, Hund's rule is up next. When electrons occupy orbitals of equal energy, 1 electron enters each orbital until the orbitals contain 1 electron with parallel spins. This sounds like a lot, but it's really not that bad when you think about it. Let's say this was the 2p energy level. So I said p because there's 3 boxes, and p orbitals or p sublevels have 3 orbitals. So if this was 2p and I was filling in my electrons, they would fill in singly first, just like you see here. And if I had another electron to place, I would go back to this one and do my 4th electron right there. Notice that they're all facing up, and then if I were to go in and fill in more electrons, I would draw them as all down arrows. Here's a little demonstration of Hund's rule. If you watch this animation a couple times, you can see them filling in. 1s, working up energy, so that's off bow. They're going in opposite directions. They're filling singly first in the 2p, and then going back and filling doubly. So 1s, and then they're spinning in opposite directions with the up and down, and then 2p, single, 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 double, double, double. All right, so here's just a quick summary of all 3 of the rules. Off bow, we know it means starting at the 1s level. Pauli exclusion says they have to be in opposite directions if electrons are in the same orbital. And Hund's rule is if there are orbitals available, multiple orbitals available at that same energy level, they're going to fill singly first and then doubly. Take a minute to look at your sheet. This same picture is on your note sheet, and I want you to tell me which one of these is correct and then what's wrong with the other 2. So take a minute to think about all of the rules, but especially think about Hund's rule in this case. If we were to start filling in electrons, there's different ways to represent the orbital diagrams. So up until this point, we've really done ones that are vertical, but you can also do the ones that are horizontal like this. The number of spaces to represent orbitals stays the same. So here's my principal energy level, and here's my sublevel, and it has 1 orbital. So that's why there's 1 blank right here. Once that one's full, so first electron, second electron would go here. I would move to my next energy level, 2, and my next sublevel, which is S. There'd be my 3rd electron, and then facing down would be my 4th. Moving over to 2p, I'm still in my 2nd energy level, but I'm in my new sublevel, p, that has 3 open orbitals. So 1, 2, 3, and I would fill in my 5th, 6th, and 7th electrons. Number of electrons, can help identify elements. If you look on your periodic table, it is easy to identify the number of electrons that neutral elements have. The atomic number, you should know, represents the number of protons. You should also know that in neutral atoms, it is the same as the number of electrons. So in this case of our first example here, there are 1, 2, 3, 4, 5 arrows, which means there's 5 electrons. If I look on my periodic table, I know this represents element number 5, boron. I can do the same thing with this next example. 1, 2, 3, 4, 5, 6 electrons. If I look on my periodic table, it's element with the atomic number 6, carbon. Why don't you try the next two on your own? Now it's time to show me what you actually learned from this note sheet and this video. So take a couple minutes. You're going to use these orbital diagrams that are on your note sheet, so you don't have to draw these ones out, to draw the orbital diagrams using arrows for hydrogen, carbon, oxygen, and sodium. These orbital diagrams go in order. Notice it has increasing energy on this side, and all of your energy, principal energy levels and sublevels labeled on here for you. So remember Aufbau's principle, remember Hund's rule, and remember the Pauli exclusion principle as you work through these four elements.